Poslední den всегда трудно. So I want to start by giving a cohomological interpretation of the veil conjecture as stated at the end of last lecture. So you remember that it was about this zeta function, which is like a generating function for the number of points over Fm, M. And it stated, I will make it for short, it stated that it is a rational function. I mean, that the formal series can be expressed as a rational function. I will rewrite the functional equation, functional equation, because I'm not sure. I think maybe I stated in the reverse. No, but the correct one is this one, n. Let's say n is the dimension of x, and t is equal to plus or minus p n chi over 2 t power chi. So I'm sorry, I have two states, two pairs of notes, and in one of the notes, in the printed version, I have switched this one. This is the correct one. So if you have the printed version, page 17, it should be corrected. I mean, those two should be switched. Okay. Well, it's not fundamental, but it's better to have a correct formula. Then there was the Riemann hypothesis. And the third one was, well, I could state it as continuity and comparison with topology. So, except for the last one, in those there's no mention of cohomology. It's just properties of the number of points over a finite field. But actually, to prove them, there's no known proof which does not use cohomology. So cohomology is something that is difficult to define already in general over the complex numbers. I will hope that you all know some cohomology, either Betti cohomology or singular cohomology. Okay. Now, in algebraic geometry, what happens is that, well, if you look at, for example, coverings, the fundamental group of a variety of a C, you can view as the group of the universal covering. But the problem is that the universal covering in algebraic geometry is not an algebraic variety, or even if it is, the morphism is not algebraic. Typically, I mean, when you look at an elliptic curve, so this would be the elliptic curve over the complex number. This would be a lattice. So this is an algebraic variety. Now, C, of course, you can see as an algebraic variety. It's the affine space. But the map is not algebraic. It's absolutely transcendental. And the same thing, it is not possible to define cohomology in the same simple way as we do over the complex numbers. Nevertheless, there is a theory, there is actually various theories that were developed essentially by Grothendieck. So I will just rely that there is, I will write like this, with space. So what I write on the, what I will write on the right will make sense only for those who have studied it, but I will explain what are the properties and how they can help to construct this. So we would start by taking the étale cohomology, so not of X, but of X with the scalar extended to the separable or algebraic closure with finite coefficients, L, N, Z. So it is a theorem that, you can construct this purely algebraically, and that it gives the same results that if you would take the topological cohomology, in case you can take the complex, and then you take the limit, the inverse limit. So let me remind you that if I take the inverse limit of Z, Z, and what I get is the L-adic integer, so I get something of characteristic 0. It's a well-known trick to start from something with, in characteristic, say, L. If you can lift successively, infinitesimally, everything, you can go back to characteristic 0. It's a possible definition, actually, of the L-adic integers. So if I take this limit, I get the ZL module. So usually what we do is to tensor with QL. So suppose we can define that. What properties do they have? Well, they are finite dimensional QL vector space. That's important. The dimension, there are 0 for I strictly greater than 2n. That's also important. They are functorial. Actually, those spaces have a double functoriality, which is very interesting. It makes this cohomology richer than the classical cohomology. So the first one is, the first one is if you have a map, so an algebraic map between two varieties. So for the moment, this is a cohomology that works for any algebraic, actually for any scheme, you can construct this cohomology. If you have an algebraic map from X to Y, you get a contravariant map. So from H, H, we'll write it like this, Hi of Y. So I'll write this F upper star to mean, upper star means it's contravariant. But it's even better because, so that's looking at maps on this space. But you can also look at maps on this space. What are maps on this space? It's a Galois group. The second thing is that the absolute Galois group, so the Galois group K bar for the K, I will write it like this, acts on this. And this makes it a very rich property. It acts on this because simply the Galois group acts on this factor, so it acts on this variety. And so the property that I take for granted, but it's much more difficult to construct the cohomology than to show that the Galois group really acts on this. So you have a natural action. It's a Galois representation. If you want, you can view this as an example of a map from this group, that I denote GK, well, to the GL of, so GL over QL. This is a fundamental example of a Galois representation. I denote GK, this group. So of course, in classical cohomology, your over complex numbers of the Galois group is 0, so you don't see any Galois action. If you're over the real numbers, then you do have a Galois action, but it's small. It's just the conjugation, the complex conjugation. So you have an automorphism of order 2, which is quite, well, gives some information. If you start with a variety defined over R, you extend scalars to over C, you have the action of a complex conjugation, and it's sometimes very useful to consider this. So that's the first fundamental properties. You have the classical result, I mean the Kuhnetz formula holds. I mean, saying that the cohomology of the product is the sum of the tensor of the cohomology. I will write the Poincaré duality. So, sorry, I should have written first, you have cap. You have a cap product also. That is, you can take, and the cap product goes from HI to HI plus J. So the Poincaré duality, it says that, well, if you look at this cap product from well, it goes to that, and it's part of the construction that this is actually a vector space of dimension 1. So I write this to say that it's non-canonical, but there is an isomorphism. So here I'm taking cohomology with I'm taking QL vector spaces. So this is a vector space of dimension 1. So non-canonically it's isomorphic to QL. And the duality says that this is a bilinear form. That's from the construction. And the Poincaré duality theorem is to say that this is a non-degenerate bilinear form. In particular, the dimension of this is equal to the dimension of that. So Poincaré duality. So once you have all this sort, it is especially the Kuhnetz. So I don't write Kuhnetz, but to have the Kuhnetz formula is essential to state what I will state. You have a trace Lefschetz. Maybe I should write. I'm not sure. Is it like this? You have the Lefschetz trace formula, which says the following, that if you have an endomorphism F from X to X, well, the number of fixed points of F, of course, in general, is not finite. There's no reason why it should be finite. But in algebraic geometry, you can always define it as the intersection of the graph with the diagonal. So this intersection, of course, is on X plus X. That's a natural definition. So what I call the number of fixed points is actually the intersection number of the graph of F with the diagonal on X. Okay? So if all fixed points are isolated and simple, then this is really the usual number of fixed points. Okay? So this number can be negative in some cases. Okay? For example, the number of fixed points of the identity is defined that way. It is the self-intersection of the diagonal. So the formula states that it is always equal, just like in topology, it can be written as a sum from I equals 0 to 2n, the alternate sum of the trace so I will drop the star and just write F, but then I will write on which space it acts, okay? So in some sense, there is something that I should call, I will write F instead of F star, or some people write HI of F. So to make the notation simple, I just call F. It's a map induced by F, but then I specify on which space I make F act. So you have this formula, and of course, once you have this formula, you know to whom you want to apply it. You want to apply it to the Frobenius map, because the number of fixed points of the Frobenius map is equal to the number of points is equal to this number of points. So before doing that, I will add one more thing. I will take, so all this is sort of general algebraic geometry. There's no need to specify on which fields I work. Now, if I work, say, over Fp, Fq, or in general in characteristic P. So I have this Frobenius map. So this one I will write F, capital F for Frobenius, or Fx if I need to specify that it is the map, the Frobenius. The Frobenius map. Then, well, I will write what the Poincaré duality states. Well, it is automatically an endomorphism of the cohomology algebra. So if I write like this, the cap product F y. Well, I know that it is a linear map, so it must be a multiple of this, and the correct multiple is p to the n. So actually, with what I have stated, I cannot deduce it, but you have to introduce the cycle map, the so-called cycle map for cohomology, and then it becomes clear. So I just state it like this. So here, this is an element in HI, and here, this is an element H2n minus I. And again, I write F, what I should write F upper star or HI of F. And what I write with this bracket is this, I mean, it would be X, Y, ascending X, Y. Once you know that it's a perfect duality, this notation is reasonable. So, once I have this property, well, what I claim is that the first two becomes very easy. First of all, the number of points in XPM is just, well, what I call the number of points of the Frobenius rise to the power m. There's one thing to be checked. So the number of fixed points is defined as this intersection. So I need to check that all fixed points are isolated. But that's very easy in this case because the fixed point in some sense is something like identity minus f. the differential of this is 0, rising to the power p in characteristics p. When you differentiate, it gives 0. So the differential of this map is identity at every point. Therefore, any fixed point is isolated. So it's funny because in many cases, inseparability gives a lot of complication in algebraic geometry, but in this case, it simplifies things. So this number of points is really this intersection number. So if you write this, you can write this as the sum of traces of Fm acting on Hi of X. Okay. Now you need the elementary, it's a linear algebra formula. I need to compute this kind of thing, the sum from m equals 1 to infinity of the trace of Fm. So I drop this part is just it's just F is just an endomorphism of any vector space. T m over m. That's very easy to show. I just explained. You do it for a diagonal map. Then it's clear. You need to know the formula that says that. I've already given this formula. That's exponential of the sum of xm over m is 1 over 1 minus x. You know that since at least first year of university. So you need this formula. If the map is diagonal, this formula gives you that. Both are invariant under conjugation. So you only need the map to be diagonalizable. And then the map that you can diagonalize are dense. So since it's a closed formula, the formula is true for everything. So this is, if you want, an easy lemma. So using this and this, you get an expression for the Zeta function, which as a product, so for I equals 0 to 2n of the determinant of 1 minus ft acting on I. So here you get, there is the minus 1 to the I here, and there is the minus 1, so you get plus 1. So this is what I called Pi in the statement of the Veil conjecture. So if I define Pi equal to this polynomial, then I get essentially the rationality statement that I gave on Sunday. Except one point, which is not obvious, is that, I stated that the rational function has coefficients in Z. Here, the polynomials that I construct, a priori, they belong to QL of T. I'm taking characteristic polynomials of something that is an endomorphism of a QL vector space. So I get a polynomial with coefficients in QL. Actually, and it is not at all obvious to show, but you can show, of course, that those coefficients are actually integers. If you already know the Riemann hypothesis, it's easy. Because, what is clear is that globally, the rational the rational function has coefficients in Q. That's obvious because the first expression here, you only have rational coefficients, so you can't get nothing else but rational coefficients. So you know that this sort of alternate product of polynomials actually has coefficients in Q. But the Riemann hypothesis tells you that those polynomials are precisely the part of the poles or zeros that have some absolute value. So each of these has to have coefficients in Q by uniqueness factorization. So actually what happens is that you need something much weaker than Riemann hypothesis to prove that, but okay, that's enough with this. And so the Lefschetz formula gives you the first part. The functional equation, of course, comes from Poincaré duality. Perhaps I'll formulate just the lemma. Okay, we'll this. Okay, it's just a lemma that essentially linear algebra. I suppose that I have, I will write it like this. Suppose that I have, a perfect pairing between two vector space. I call B the dimension of D. And suppose that I have something like this, that f of V, G of W gets multiplied Can you read this? Okay, I suppose that this acts like a similitude. Then there is a relation between the characteristic polynomials. The characteristic polynomials of TF. So I've given different letters, so I don't need to put it, of course, on V or W. So it's minus alpha T to the power B. Here you have the determinant of G minus 1. And here you have the determinant of 1 minus G over alpha T. So I'll leave this as an easy exercise. So if you apply this to the Frobenius on the Poincaré pairing, you get exactly the functional equation. Well, you apply this to each of the HI, you take the product, and that gives you the functional equation. Now, so I won't explain the proof of the Riemann hypothesis, because that would be a whole course. I could have chosen to do only that during the week, but I chose to explain other things. I will explain the continuity statement, at least for without giving proofs. So I will explain this, what I mean by continuity and comparison with other topologies. So it's a bit different. It's two things. So if so the first thing is comparison with topology. What do I mean by this? Well, suppose that so X is defined over some field, and essentially it's a field of characteristic 0, and I can embed it into the complex numbers, which is the case of, well, in algebraic geometry it's always the case, because if K is of characteristic 0, you can always define X over a finitely generated field over Q, And finally generated field over Q you can embed into C. That's the so-called Lefschetz principle. So it's not a very, essentially the only hypothesis here if we have characteristic 0. Then I have two things. I have, on one hand, I have, well, what I have written like this, which is a QL vector space. And I have, well, the cohomology of over complex numbers. So I should write an index. I have fixed an embedding. A priori, this variety depends on the embedding I have chosen. Of course, if I can modify it, but I do it for one fixed embedding. So they're certainly not equal because this one is a QL vector space and this one is a C vector space. But what can I do to compare them? Well, I can be further non-canonical. This QL I can embed into C. So that's highly non-canonical, but the sort of the miracle of the theory doesn't really depend on the embedding. And then I can tensor this with C over QL. So the comparison theorem says that now those two spaces are the same, or are the same. They are isomorphic. In particular, they have the same dimension. Well, not really, because well, you can't compare. I mean, you can't compare QL and C. The only way to compare them is to embed one in the other. That's the other thing you have to keep in mind is just a simple algebra thing: is that any homomorphism between fields is always an embedding. So actually, what I'm writing here is a homomorphism from QL to C. Otherwise, I mean, they're not the same object. You have to put them first in the same category, and then you can compare them. So the way to prove this is to prove this on the finite level. So you, instead of taking the limit first, you do it over Z over Ln Z, and then you show that the coverings are the same, so those two things compare well. And then you take the extension. So that accounts for the comparison theorem. So it tells you that, okay, if you're in characteristic 0, so you can always view your variety as defined over the complex numbers, then taking étale cohomology or taking the classical complex cohomology will give you the same space. That's what it tells you. So that's for the comparison. What do I mean by continuity? There is a classical fact also due to Lefschetz. Is if you have a smooth family of projective variety, meaning that each fiber is smooth, then the cohomology doesn't change. More or less the dimension of the cohomology doesn't jump. Usually in a family, only the Euler, the Poincaré-Euler characteristic remains the same. But if you have a smooth family, then each of the cohomology remains the same dimension. So a similar property is true for étale cohomology. So I will state it like this. I will take, well, for once, I will take S, in French we call it a trait. I think in English or in Russian we use the same word. It's a Grothendieck word. What it means is the spectrum of a discrete valuation ring. Or if you want, it's a ring that has only two ideals, 0 and maximal ideal. So, a trait. trait. It's a French word, but it's used, I mean, it's Grothendieck terminology, so I don't think it's translated in any language. It means a short line. This is a trait. So what it means is that if I write, so S essentially has 2 points. It has a generic point and a special point. So example, well, ZP has just two prime ideals. The prime ideal 0, which corresponds to the generic point, and the ideal PZ. Okay? And, well, it's classical. It's nice to formulate the properties of deformation. What you want to do is when you go from the generic point to the special point, what happens? That's what it means to study deformation. So you can always reduce to this case. And in this case, what it says is that at least if everything is smooth, so I will make this picture. I suppose I have a scheme X over S. Then I have, well, I have like a big point. I mean, this point is not closed; it's dense, and I have the special point. So usually, well, it's not hard to suppose that you have the generic fiber. So this, you always assume it's smooth, and you have the special fiber. So the special fiber can very well be singular, can be something like this. This would be XS. So in that case, it's not possible that the cohomology remains constant. It's already not true in the complex case. But if you assume that this reduction is again smooth, then the property is that the cohomology essentially remains the same. So you have, so if X over S is smooth, so that means essentially it means that XS is smooth. Okay? So I'm asking much more than a regular, because the scheme could very well be regular and this special fiber singular. So it's much stronger than regular. So in that case, you have, well, you have a comparison map from xi at xs, and it is an isomorphism. That's what the continuity property says. And further, you can, I mean, this map is functorial in the following sense. Suppose that I have, well, suppose that I can define, well, a morphism. So I will write it, if I want to write it the other way around. Suppose that I have a morphism of S scheme. Then I get a map here, which is I will write F beta to hi y eta. I get this isomorphism, and I get, well, with I hope obvious notation, F eta is the restriction of this morphism to generic fibers, and Fs is the restriction to special fibers. Then the statement is that those two commute nicely. Well, the statement is not surprising, but it's very useful. So that's really that's a kind of full statement of what it means that cohomology is continuous.
Let's say X is an elliptic curve. It's an elliptic curve. It's an elliptic curve. If I
Yeah.
similar less cohomology
Yeah.
because they are certain.
Yes. Okay. What happens is you still have a map like this, but it's not injective. So let me repeat this. In the picture I have drawn, this statement will be false. Okay, with the picture I have drawn, this statement will be false. Okay. Now, if so, I don't do the drawing, but it's only if the reduction is smooth that I get. Otherwise, I just get maps. There is a map that way, but it's not injective. Okay, is that clear? So, if you look at this now, it's tempting to interpret the Frobenius. Suppose we have maybe now I will erase this. Okay, sorry. So this last part of the Weil conjecture, I hope now it's clear. Why the degree? So the degree of the polynomial that occur here, of course, is a dimension of the eternal cohomology. And so with those comparison theorems, well, with both comparison theorems, if you have a variety in characteristic over Q in characteristic 0, maybe I will redo the picture. I will erase that as time to dry. Okay. Now, suppose that I start with x over q, and I suppose that it has with smooth reduction that I call xp. So this means that there is, I'm working with projective smooth varieties. So this means that there is a scheme over Zp that extends X and with smooth special fiber. So the first, the continuity of the cohomology will tell me that the cohomology of X is isomorphic to the cohomology of Xp. That's the continuity. Both are QL vector space. Perhaps I should. They are QL vector space. And the comparison theorem tells me that if I tensor this one with C, well, I get something that's isomorphic to well, the classical either Betti or Durham or singular cohomology. So that's the comparison theorem. So of course, I hope that clearly explained fully why the dimension, why the degree of the polynomial pi, which is the dimension of this vector space, is equal to the topological Betti number. Now I hope obvious. Now I want to to apply this diagram to the situation of the Frobenius. So I take again this image. So on this space, I have a Frobenius, which is just rising coordinates to the power p. So I would like to lift it to characteristic 0 in order to apply this. So I would be able to write this characteristic polynomial as a characteristic polynomial on this cohomology. Now, I will explain how this is possible. This is basically classical algebraic number theory. So it's a reminder what is, inertia, decomposition group, and Frobenius in characteristic 0. I put that between quotes, so I'm not sure everybody has seen that, so I will quickly recall. So actually, you have to do it for infinite Galois extension. I will just explain to finite Galois extension, and then you take the limit. The situation is the following. You have a finite extension, say of degree d, a number field, and you suppose that the extension is Galois. I take P, a prime of K. So I remind you what it means is just a prime in the ring of integers, and it lies above some prime number, which means just that P intersected with Z is PZ. Then you can do the following. First, you define the decomposition group. So the decomposition group, actually, I will try to make, depends on the prime ideal. It's just a set of sigma in the Galois group that fixes the prime ideal. There are various prime ideals above P. Like above a curve, there is, if you have a curve covering above one point, there's several ones, and all of them are muted by the group of the covering, here by the Galois group. But there is, the subgroup that fixes P. Now, for this one, you can for sigma in D, you can reduce it mod P. This means that, you have OK. Any element of the Galois group sends an algebraic integer to an algebraic integer. But now, if you reduce mod P, well, you need exactly this condition for this map to be defined. So let's call it sigma tilde. So you get a map from this decomposition group to, automorphism of this finite field. This is nothing else than the Galois group. Perhaps I will denote this as it's a finite field. I will denote it Fp, so of Fp over Fp, because any automorphism fixes Fp. So this is just this reduction map. What I define as the inertia is just the kernel. Actually, this map is surjective. I don't need it here, but so we have this picture. So you notice that by construction, IP is a normal subgroup of DP. it's a kernel, so it's a normal subgroup. Now here, I have a canonical element. Let's say that I call, well, let's call it FRP. So I can lift this to an element that I will call Frobenius of P. So it is characterized by the property that maybe I will write it here, is that Frobenius of P of X is congruent to X to the P modulo P in some sense. So there is a Galois. So the problem, there are two little problems, is that actually I would like to define this in terms of just the prime number P. So there are two things. If I write this element from P, then I'm abusing mathematics. But it's not too serious. What I'm abusing, it's defined. Up to is well defined. Up to two things. First, conjugation. Okay, this is just an elementary thing, is that if I change prime ideal, let's say if I take P prime equal tau P, then everything is conjugated by tau. That is, I mean, the new decomposition group is just a conjugate. The initial group is also the conjugate, and the Frobenius is a conjugate. So I get a well-defined conjugacy class. But it is also defined only up to the inertia group, because, well, I have the choice here of this element. I mean, I can multiply by any element from the inertia group up to inertia. But still, what I can do, perhaps I will erase this. So if I get back to the case, well, exactly this case, perhaps I will, well, I keep this. If I go back to this case, I have a variety defined over Q with smooth reduction. It is very important here that the reduction should be smooth. Then I claim that I have, well, I have this Frobenius of P acts on, well, the cohomology of X. And, well, the reduction modulo P of Frobenius P by construction is the Frobenius in characteristic P. So I have something I will call, well, the Frobenius at P acts on HI of XP. So Frobenius is just rising to P's power. Now, according to the continuity theorem that I have stated, I claim that, well, the determinant of 1 minus the Frobenius at P T, so over X, So this is for the variety defined over Q, should be equal to the determinant of 1 minus, well, this Frobenius T over Hi of xp. Now, okay, sorry, it's clear. First, I should first write, I will write the little p later. First, okay, this is clear because I choose an element here that satisfies this, and then I get that. So this is my continuity of the diagram that I have just erased here. Now, what I want to be able to write is, well, I want to be able to write this. That is something that depends only on the prime number p, because I don't want to choose each time a prime ideal. So I have to look at those two conditions. So this element is just one of all the Frobenius that I get if I change by inertia group by conjugation. So it's obvious that changing the element by conjugation doesn't change anything. When you take a characteristic polynomial, it's of course invariant under conjugation. Now, the inertia, that's a little more complicated. So I will state a general property. So remember, I will state just a definition. Suppose you have a representation. So I take over Q, but it could be defined over a number field, so a Galois representation. Any coefficients for the moment. So GQ is the absolute Galois group. It should the Galois group Q. Well, the definition, rho is unramified at P. This is a definition. If, well, the image of inertia is reduced to 1. So I have defined inertia only for finite Galois extension, but if you want to define it for an infinite extension, you just take the limit of everything. So this is just a definition. Okay, it means that the subgroup defined by inertia acts trivially. Now, you notice that the inertia group is well defined up to conjugation, and this definition doesn't depend, it remains the same. I mean, if the image of I is trivial, the image of any conjugate subgroup will also be trivial. Now, the claim is that what is true for for all the interesting, it's not true for all representations, but for all the interesting representation, this is always true except for finite number of primes. For the moment, it's any vector space. Yes, it's not important here for the moment. This is just a definition. Now, the main claim is that if X has good reduction at P, so having good reduction, I have already explained that, means there is a scheme that extends X with a smooth special fiber. Then, well, the HI X is unramified. At P. Or, if you want, the inertia groups act trivially on the L-adic homology. This is not at all the hardest part in the theory. I don't prove it, but it's not that hard. So, with that property, what you get is that, well, at least in the smooth case, this is well defined. That is, I can erase this. So if the special fiber is smooth. Okay. So this gives us actually two things. First, well, it gives us an interpretation of the Hasselbalch P factor, at least for all the P's where the representation is unramified, that is at all the places of good reduction. That's the first thing. The last thing then is that it gives us an idea of how to define the factor when, well, when the reduction is not smooth. For that, I will use the following elementary algebra lemma, I will call it up. Is that correct? No? Isn't suppose you have, well, I take a group that I call I, G, and a representation, again, it's linear algebra. Suppose I have an element F that normalizes I. So these are the hypotheses. Well, I denote, well, it's classical to denote that the subvector space that is fixed by I. I mean, so the V's in V, such that for all I in I, rho I V is equal to V. This is the setting. Then the conclusion is two things. First is that, well, F stabilizes this vector space. It's a very easy lemma. Huh? It's not a difficult exercise. And, well, if I take another element, say G, which belongs to the coset I, well, that one is almost trivial, is that if I restrict this to Vi, or I restrict G to Vi, the two are equal. So that tells me how to define so after having done all that, I can finally come back to the, well, what I had defined initially as the zeta function. I will define the zeta function of x over q s. So certainly I want to define it as an Euler product. So I know more or less what should be the Euler product, except at a finite number of places. I explained that. Certainly, donc, if I want to write it like this, a product over P of local factors, but here I remain over Q. Certainly, if XP is smooth, perhaps I know I should erase before so it gets dry. I keep that and I'll so if XP is smooth, I will define ZP of X over QS. Well, I will define as the veil zeta function of XP with P minus S. This is a perfectly reasonable definition and it coincides with what I had introduced before. So in that case, it will be, with what I know now of about what we know about veil zeta function, you can write as a product from I equals 0 to 2n of, well, the determinant of 1 minus, so with my notation it would be FRP, P minus S, so HI of X, P, minus 1. No, sorry, you have here the alternate product, so it's I plus 1. So you know by what we have explained that this is the same as the product of something in characteristic 0, that is, you take the determinant of 1 minus, so the Frobenius at P, P minus S, acting so on the cohomology of X this time, minus 1 to the power I plus 1. So it's natural to call, I mean, to group together the factors coming from the cohomology. And so I will define L, so the L factor as a product over P of L P X S. So in such a way, so I need to define, of course, the local factor. So the definition for primes of good reduction is easy. It's this one. I define it as the determinant of 1 minus the Frobenius at P of P minus S HI of X. So I put the minus 1 because all of them are with minus 1. So that definition is perfectly okay for primes with smooth reduction because they are unramified, so the inertia doesn't mess up. Now, the little lemma that I have raised tell us what to do when the inertia acts non-trivially. What should we do so that this doesn't depend on the element chosen modulo inertia? We should add here fixed by inertia. So if I take the sub-vector space fixed by inertia, so I write it in a different color because, okay, you don't need to put the I for almost all primes. Only for a few primes, you need this factor because the cohomology will be smaller, and that's the way we define this. And then, in the end, we define the Hasselbalch zeta function as the alternate product of those Li. So the product from I equals 0 to 2n of L hi of x s minus 1 to the I. Okay. What I want to do is, okay, so this is the general theory, the general theory. By the way, those formulas those definitions were given by Jean-Pierre Serre. So I want to explain just in detail the example of an elliptic curve over Q. That's where you see enough. But what I wanted to do in some sense is to motivate this definition, to see where it comes from. Because that's usually not written in the literature. And you can find this definition, and the first time you see it, you wonder why define it that way. I hope it's clearer like that. So I have all the main formulas here. So what does it give for an elliptic curve? So the example an elliptic curve E over Q. So what's special? So the dimension is 1. The genus is 1. So you have the dimension is 1. Of course, the dimension of H2 is also 1. And the dimension of H1 is 2. Twice the genus. So it's 2. If you know some topology, you know already that. So the zeta function of E over Q over S. Well, I take first the definition. So it's L of H naught of E S, L of H1 of ES, sorry, H2 over L of H1 of ES. Now, of course, there is, this is the same as the cohomology of a point, so we've already computed that, that's zeta of S, and this one is just the one translated, so it's zeta S minus 1, and you end up with, well, what is usually denoted like this. This is just a notation. It's equal. So this is the usual notation for what is called the L function of an elliptic curve is actually the L function of the H1. So I drop the H1 because there's only one interesting, so I call it LE. So there remains, well, the zeta function we already know, even if we don't know everything about it, we know a lot. Zeta of S minus 1, 2. So we need to see what is this LE of S. So, well, we can write most of the factor easily For P good, well, we know that zeta E P of T, well, it's something that can be written like this, 1 minus PT. We know this coefficient, it's a polynomial of degree 2, and the last coefficient has to be P. So there's only, I will write it like this, minus AT. We only need to know what is this coefficient little a. So that's from, well, the Veil conjecture that was already proven by Hasse in this case. We know that it has this shape. And now a little computation will show you that this little a, so AP, I mean, we should call it AP, it depends on P, is that AP is just the number, sorry, it's easier to write it like this, the number of points of EP over FP is P plus 1 minus AP. That, of course, gives a definition of AP, but it's easier to remember it that way. So I know what is the factor of this. Well, it is this factor at P minus S. Because these two account for the zeta of S, zeta of S minus 1. So LP is just 1 minus AP P minus S plus P 1 minus 2S minus 1. So that's for P good. I get this formula. Now for P bad, of course it's more complicated, and I can't give the full computation, I'll just give the results. But you know that you get a cohomology of smaller dimension, so you'll get a polynomial either 1 or a polynomial of degree 1 in P minus S. So the result is the following. You have to know something, is that the reduction of an elliptic curve, so the bad reduction, gives either a cusp, like this, and in this case, we say that we have additive reduction. The reason is that you don't get a group law on the whole curve, but if you take away the singular point, you still have a group law on this curve. And in that case, it turns out to be isomorphic to the additive group. That's why it's called additive. And the other possible case is you can get a node, and in that case, you get what is called multiplicative reduction for the same reason. The point is that if you remove this point, you still have a group law on this curve, and this group is, at least over the algebraic closure, is isomorphic to the multiplicative group. Now there's two subcases. It can be split or non-split. What does split, non-split mean? You have two tangents here. And so the curve itself is defined over Fp. This whole picture is over Fp. So as the curve is defined over Fp, the pair of tangents is defined over Fp. But individually, they could be defined over a quadratic extension or be defined over Fp. So split is when the tangents are defined over Fp, and non-split correspond to the case where T2 are defined over Fp squared. They are defined over a quadratic extension. So there are the main two cases with this subdivision. So the local product can be expressed like this. Well, it's 1 for in the additive case, additive reduction, so that's simple. It's 1 minus P minus S minus 1 for split multiplicative, and it's 1 plus P minus S minus 1 for non-split multiplicative. So at least in principle, so where does this computation come from? Of course, either you can take that as a definition, or, but then it's not obvious that it coincides with the definition that I have given. That's a computation of local homology. That's not that easy. Well, homology for the special fiber. Okay. It's, I mean, what I claim, what I don't prove, but I claim is that this formula is exactly the formula given by this. Well, you need to know a little more than what I have explained. If you know a little more, yes, you can do it. Sorry? Well, you need to know how to write the action of inertia on the H1 of an elliptic curve. What is the inertia on the Tate module? Also, in the maybe I can say that in the case of elliptic curve, what do I want to erase? There is a very concrete description of Vital homology. I should perhaps have started by this. If I denote, let me write En as the kernel of multiplication by n. So from E, I write K bar because the definition makes sense over any field. So if you are over the complex number, it's obvious what I'm going to write, that this is isomorphic to Z over NZ squared. Over the complex number, it's easy to see that. And it's not true, well, if the characteristic of K does not divide N. It's not true when the characteristic divides N. Then you can do the following. I can take this for L to the N. Then I get Z over Ln Z to the square. And I take the inverse limit. And I get what is called the Tate module, which is something, well, as a group, it's isomorphic to ZL squared. If you want QL vector space, you cancel by QL. Now, what is nice is that the Galois group acts on this. GK acts on it. Well, it's clear because if I have a point that's killed by n, any conjugate will again be killed by n because the multiplication by n is defined over little k. If my elliptic curve is defined over k. So this gives me a good candidate for the homology. Well, for some obvious reason, it is not the homology because this is clearly covariant. If I have a morphism from E to B, I get a morphism from TLE to TLB. But never mind. It's a homology, or if you want, the homology is a dual of that. So, in fact, so of course, those were defined much before the long time before the L-adic homology, and they were the first example. So the étale cohomology, so if I write cohomology of E, well, it's a claim, it's just a dual of that. That is, it's the homomorphism of a QL. So from TL of E tensor QL with value in QL. Huh? Oh, well, yeah, well, there is a first obvious definition is that you take the dual of the homology and you call it a homology. Now there is, I mean, people have constructed homotopy étale homologies, this kind of thing. So yes, you can, well, there's two ways you can do. You can define homology as the dual of the cohomology. So that's a reasonable thing. Now, if you want to construct directly the theory of homology, it's more complicated, but that can be done. And they don't always match. They match for smooth projective varieties, not otherwise. So certainly in the threatening volumes of SGA, and I mean, there's a whole series of papers written by Maser and Lichtenbaum. But for the part that I explain, this homology, when you construct it, is the dual of the cohomology for smooth projective varieties. So this makes the cohomology for elliptic curves or for abelian variety much more concrete. And what you have to do is you have to understand how the inertia acts on this, and that will enable you to compute this formula. So, oh, no, inertia, that's not true, that you cannot compute. You know a lot of things about inertia. Well, first of all, okay, what is complicated? I have not introduced tame inertia and wild inertia. Wild inertia is very complicated to compute. But here, you're allowed to choose any L. So essentially, you only have to look at the action of tame inertia. And that's fairly computable. So perhaps I will finish this lecture just mentioning, so that's what I will explain in the afternoon. Now, what would be the functional equation for this L function? Well, it's a theorem of Wise. That if I define, well, there is an integer which is the conductor of the elliptic curve, which is a well-known invariant, such that if I define lambda E of S, so I put this conductor S over 2, I put a gamma factor, which is 2 pi minus S gamma S, L S. So that's just a definition of what should be the functional equation in general. And the theorem of Wise is that, well, there is analytic continuation, so L S extends to an entire function. So a priori, this Euler product is only convergent, actually. So the product is absolutely convergent for real part of S, strictly greater than 3/2. That's not difficult to prove. I could leave it as an exercise. It's not at all obvious that it extends further. So part of the theorem is that it extends as an entire function, and it satisfies the functional equation lambda of 2 minus s is equal to plus or minus lambda of s. So this is not formulated like this in words, but this is a consequence of the Taniyama-Shimura-Veil conjecture. And that's what's proven in Weil's paper. Essentially, what Weil's proves is that E is modular. So E is an elliptic curve over Q. I should perhaps mention that there is an entirely analog conjecture for elliptic curves over any number field with more factors, and then the L function should do the same, but that's not known. Essentially, we know this functional equation and analytic continuation only for CM, I will write it like this, CM varieties. That's Shimura. And modular varieties, so I don't define what this is in general, neither CM. So in those cases, we know analytic continuation and functional equation. That's a very restricted category, but it's still a very interesting category. And Weil's theorem is to show that an elliptic curve over Q is modular. So what I will do in the last lecture is explain what this means and why, if we know it's modular, then, well, the classical theory proves the functional equation. So I will prove at the same time the functional equation for the zeta function and for this function, but granting that it is modular. Of course, to prove that it is modular is the whole paper of Weil's, which relies on many other papers that would be too long. So I should stop here.